Welcome to section 15.2, Displaying Data and Interpreting Data Displays. We'll be covering these topics and objectives, standards, vocabulary, and concepts. So every day we see the results of surveys in newspapers, all over the internet, TV, and sometimes we've got numbers. So when we think about numbers, we're talking about the count or percentage. But other times we might be shown a table, a chart, or a graph. And these can help us get a sense of what the data means because a chart or a graph can show us the big picture. Now, we're going to study common data displays as well as different types of questions we can ask about data displays. Interpreting data can range from reading information directly off a graph to comparing and combining this information to think about implications. So we produce data displays to help us analyze and interpret results, but not as the end goal in itself. So we have to learn to read and interpret data displays. And we're also going to examine some common errors and misleading practices. So there are different types of displays appropriate for categorical and numerical data. So when we display categorical data, we might see real graphs, pictographs, bar graphs, or pie graphs. So a real graph, pictograph, and bar graph. Let's look at a real graph is an object graph. So if you actually look at the beads here, that's where we actually use pictures of the items, or the actual items. A real graph is the actual graph. So here we actually have the beads. But a pictograph, and we'll see an example in a moment, might take a real graph but use icons or pictures of the object. So if we had pictures of the beads. So we can use real graphs and pictographs to show how a collection is related. Suppose we have a tub filled with small beads that are alike and we scoop out and they have different colors, yellow, pink, purple, and green. We mix them up and scoop them out. How many beads of each color do we have? Which color beads do we have the most of? Which do we have the least of? So we can answer all those questions quickly by looking at the real graph, by putting these beads into a real graph. Here, we're looking at a pictograph and a bar graph. A bar graph is essentially, or a bar chart, is just a streamlined fused version of a pictograph. So instead of these individual pictographs, we're going to put them all into a single bar. So you can see the relationship between a real graph, pictograph, and bar graph. So again, if we want to represent a large number of objects in a pictograph, it might make sense to allow each icon to stand for more than one object. So if you look here, we're having this little person represent 1 million. And how that relates to the bar graph is that we would take the axis and label it millions, and then this would be 2 million, 4 million. And so we don't have to just label it one piece at a time, like a real graph would need each individual person standing on a line. So to compare the populations of states, here we go. And this is super precise, right? There's no way on our graph that we can show it so precisely. Wyoming is about 500,000, but you can see that we've got almost half there and almost half there. So even though a table is more precise, we can get a sense of things by looking at the pictograph and the bar graph. A double bar graph can compare more than one category at a time. So if we're talking about people, we could do male and female, and we could compare their earnings. We could do 7th and 8th graders. There's lots of things we can compare, and it's nice to have them on the same axes there so we can easily compare the difference. All right, let's do an example here. So the bar graph shows the average length in weeks of growing seasons for 8 cities. So it's always a really good idea to read. So we've got weeks, 0, 10, 20. We've got season, and we've got cities. So we always want to make sure we're making sense of our graph first. Which city has the shortest growing season? So that should relate with the shortest week, which is the shortest bar. And that would be city C. How long is the growing season for city D? So I'm going to look at city D, and that correlates down to 30 weeks. Does city G have a longer growing season than city A? No, because city G goes to right there and city A goes to there. Let's look at another example. 5 coins are tossed 62 times. A distribution for the number of heads obtained is shown in the following table. Draw a bar graph. So these are what we've got. We've got number of heads and frequency, and we're always with bar graphs going to put frequency going on that y-axis or over here. So this is our frequency. And we've got our number of heads. So our number of heads are 0. Oh, that's just such a terrible. Use a ruler, right? 0, 1, 2, 3, 4, and 5. I got those right from there. Now our frequencies span from 1 to 20. So maybe I'll go by tens. 10, 20, 30. And maybe I really should have gone by 5s, right? So 0 goes with 3. So there, 3, that would be, let's draw 5. So 3 might be right there. 1 head goes with 11, a little more than 1. 2 goes with 20. 3 goes with 18, a little bit less. 4 goes with 9. And 5 goes with 1. And so we can see quickly at a glance the comparison between these. The graph below shows the number of marriage licenses issued over a 6-month period. How many licenses were issued in July? Each circle represents 20,000 licenses, and we've got the marriage licenses issued and months over here. So they asked about July, so we're looking at July. So that has 1, 2, 3, so that and a half. So that has 3 circles plus a half a circle. Well, how much is a circle worth? 20,000. So that's 3 times 20,000 plus a half of 20,000. And there's another way to think about this too. You could say, okay, 1, 2, 3 and a half. So that's 20,000 plus 20,000 plus 20,000. And maybe you just know that that's 10,000, right? So you could think about it in different ways, but the answer here is going to be 60,000. Oops, sorry. 60,000 plus 10,000 is going to be 70,000. You could also say 20, 40, 60 plus half, 10, right? There's lots of different ways to make sense of these. Go ahead and give these a try. Press play when you're ready to see the solution. And there we go. A pie graph, pie chart, or circle graph subdivides a circle to show how data falls into categories. This shows a pie graph of how U.S. firms in 2015 were divided according to how many employees they had. We can see at a glance that about half of the firms had fewer, so here's about half, 56, and this is this color, so it's 1 through 4, that half of the firms had fewer than 5 employees, and a quarter, so about a quarter had 10 or more. So if we kind of look at this whole section as a quarter, we would say that's 10, 20, 50 or more. So 10 or more had about a quarter. And when you think about a pie graph, I always like to take a blank one and kind of imagine it subdivided like this. And you're kind of always comparing it against these pieces, 25%. So you can kind of in your head when you're looking at this, kind of compare it into those pieces. Give this one a try, press play when you're ready to see the solution. There we go. So we've covered categorical data displays. Now let's talk about numerical data displays. We can display numerical data with dot plots, histograms, stem and leaf plots, which show how frequently certain numbers or intervals of numbers occur, line graphs, which show how data changes over time, and scatter plots, which can investigate relationships between 2 kinds of data. And then in the next section, we'll also talk about that you can use a box plot as well. So we've got different data displays for different types of data. A dot plot or a line plot is a kind of pictograph in which the categories are numbers. So these are, the categories are numbers. So instead of saying pink, purple, green, they're numbers. And we use a dot or another icon. Sometimes you might see like an X, okay, but usually you see a circle. And the dots function as tally marks. So the way you read this is you've got 1 16, 2 17s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 18s. And you could also say that would be the same as 16, 17, 17, and then 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then continue on. So dot plots and line plots, here's an example. So if we've got black-eyed peas and a measuring teaspoon, how many peas are in a teaspoon? That's the question. We can scoop out a teaspoon and count it. And if we do it again and again, we may get different numbers. So the following numbers could be something we get from different trials. So here is the data, and then we organize it in the dot plot. So we already looked at this dot plot. So we could say, okay, I'm going to draw an 18 dot. I'm going to draw a 19 dot. I'm going to draw a 19 dot, and I'm going to draw a 17 dot. I'm going to draw a 19 dot, and you continue on in this fashion until you've gone through all of them. And we can also use dot plots to record intervals as well. So if you notice on this data, this is the number of cities between 0 and 9, 10 and 19, 20, so that we're not just saying a specific number, but we can group them by intervals. So when we come back, we'll do some examples. Oops, there we go.